and yeah, so I'm going to tell you about local certification, which is one of my area of research. And the gem I'm going to talk about is how do you certify the spanning tree? So we'll come to that very soon. And then towards the end of the talk, I will tell you a bit more about what's research in local certification now. But okay, this will come in a second time. Okay, so I want to start this talk with some disclaimers. So first, okay, it's a gem talk, so I did not invent what I'm going to talk about. So yeah, it's a celebrated result, like actually a set of super nice results. Okay, the second disclaimer is that I will focus on the ideas because I think this is the thing that is the easiest to give to people who do not work in the same area. So this means that there will be maybe less definitions, less model, and that I will be a bit like hand waving and lying a bit. So sorry for people working in the area. Sometimes it will, sometimes I feel a bit strange. And okay, and also I will not cite so many papers, again, because I think that's not something that is immediately useful for people who are not from this exact area. But still, I want to cite two important papers. Of course, there are others, but I want to single out these two papers. So one is Memory Efficient Self-Stabilizing Protocol for General Networks. And what I will talk about more precisely on spanning tree, it originates from there. And the other one is Proof Labeling Scheme, which gives the more like general framework for local certification. Okay, but without further ado, let's dive a bit in what I want to tell you about. So I will consider distributed computing in a network. So you can think about the internet, and in the internet you have machines, and they are linked by cables or whatever communication channels. And I will represent that by the simplest thing you can imagine, which is a graph. So you will have just vertices that are the machines, and then the edges that are these communication channels. Okay. And one more thing in the model is that there are unique identifiers. So just like in the internet, every computer has an IP address. Here, every node will come with a unique ID, which is, well, its name, it's unique to it. Okay. And that's all I want to say about the model, nothing. But okay, if I look at this network, like we do now, what you see is the full network. So this is what you see if you are the engineer who is building the network, or if you are from the outer space and you see the full network on the planet. But what you see at the level of the machine is something that is much more restricted. So if I zoom in to this machine with identifier 18, what I see is a few other machines to which I am linked by a communication channel. So for example, I know that there is a machine number 10 to which I can communicate directly through this one communication channel. Okay. And why is this important? Because in this talk and in general in the study of locality in distributed computing, there is the idea that what you can do by communicating with your neighbors, that's somehow cheap. And if you need to communicate with the full network with nodes that are very far, this is expensive. So somehow you want to keep just communication to something that is local, to just your neighbors or the neighbors of your neighbors, etc. So just keep in mind that in this talk, the neighbors, communicating with the neighbors, that's what is cheap, that's what is efficient. Okay, so we'll come back to this. Okay, so now spanning trees. So I guess the huge majority of you know what is a directed spanning tree, but still I will define it properly. So a directed spanning tree, it's a set of orientation on some edges. So a set of pointers, here the blue arrows on my drawing, such that the three properties hold. So these three properties are that there is exactly one outgoing pointer per node. So each node has one pointer that is outgoing. Maybe there are several that are ingoing, but just one outgoing. And there should be no cycle. So for example, this picture shows something that is not a directed spanning tree. And finally, it should be connected. So for example, this has no cycle, but still it's not a directed spanning tree because it's in two pieces. You see that there is no pointer between the nodes that are on the right and the nodes that are on the left. And this, again, is bad, so you should avoid that. So again, a good directed spanning tree is something like this, with one out pointer, no cycle, and connect. Okay, so now, why do I tell you about directed spanning trees? One reason is that it's like essential in distributed network computing because it's a primitive that allows you to do many other things. So here are just two things that come to my mind when I think about directed spanning tree. One is broadcast and convergecast. If you want to send a message to all a network, then maybe what you can do is just send in to your neighbors who send in to their neighbors, etc. in the graph. So you do some kind of flooding. But if you do that, a lot of messages will be useless because you will give some information to someone who already has the information, etc. If you do it along the edges of spanning tree, you will just use the right amount of messages. So that's one reason why it's good. And the other reason is that if you have a directed spanning tree, then there is one node that is special, it's the root. There is exactly one node that is the root, and that's cool because in distributed computing, we like to do leader election, and the root is a good candidate for leader election. So just a feeling of why directed spanning tree is just like not a random structure, it's really something that is essential. Okay, so now, again, I would like to take the point of view of a machine. Okay, so this was like what the directed spanning tree looks like at the level of a network, but now I would like to take the point of view of a machine. So if I am a machine, and suppose there is a spanning tree that has been computed, the nice thing is that this spanning tree, it's not like a structure on top of a network that is a global thing, like actually it is, but you can distribute this data structure, which means that it's possible for every node to hold a little piece of the data structure such that globally it builds the full tree. And what is this little piece? It's just one pointer per machine. I said that for a directed spanning tree, you need that there is one outgoing pointer per node. And well, that's exactly what a node will have in its memory. So for example, this machine 18, what it holds of the spanning tree is this one pointer that is pointing to the machine number 10. So it knows that in the spanning tree, its parent is this machine number 10. Okay, and maybe if it communicates with this machine 15, it knows that it is itself the parent of the machine 15. Okay, so that's very nice. That's the good news, that you can encode locally the directed spanning tree. You don't need something global, or you need really little memory per node. The bad news is that this is not fault tolerant. Suppose you have this machine 18, and now you have suddenly you wake up at night and you have this doubt, like, does the set of pointer really encode a directed spanning tree? And now there are things you can check actually. So for example, you can check that you do not have two pointers. You can check that you have only one pointer to another machine. That was the first property, and this you can check locally. Just inspect your memory and you see that. But now something you cannot do is to detect whether there is a long cycle. I mean, you can do it, but this will require you to communicate with nodes that are very far away. And we said that this is expensive. So you cannot, in a cheap way, check that there is no very long cycle in the set of pointers. And you cannot check either that it's connected. Okay. So in other words, local checking is impossible. Okay. And this is sad because it means that you are not tolerant to faults. Like you cannot be sure that what you have locally globally makes sense. Okay. Okay, so this is sad, and we want to have a solution to this problem. Okay, and the solution to this problem, or at least one solution, is to keep more information in memory. Okay, so what the standard algorithm does is that it solves the problem at hand. So if you are building a spanning tree, what the algorithm does is that it does some communication, some computation, maybe there are a lot of messages, etc. And at the end, it gives to every node, okay, here is your pointer. Okay, so in memory, you have the output, and that's it. And this, as we said, is not enough to be sure that the output is good. So now what I want is that the algorithm not only will give me the output, like we give to every node the output, but also it will keep in memory some useful information that are, that are useful in the sense that they allow you to check this output. Okay. So, okay, here I call it this certifying algorithm, but it will have other names later. Okay, so some useful information that allows to do something with the output, to check things. Okay, so this is like the general idea. And for directed spanning tree, what it means is that in addition to the pointer, I will require that the algorithm give me some label with some information. Okay, so this is a bit abstract. So let's see what it means for the spanning tree. Okay, so what are good information that I can leave in the memory of a node to allow them to maybe check that that what they have is really a spanning tree. And here there are two pieces of information. The first piece is the distance to the root. So I have this machine. It knows that it has a pointer to this other machine, and now I give it this information in memory, this additional information, which is that its distance to the root when it follows the pointers is 2. Okay, so it means that this machine, it has to jump. If it could jump, it would jump two pointers to reach the root of the spanning tree. Okay, so that's one information. In other words, one other way to see that is that it is given its depth in the spanning tree. Okay, so that's one information that you can write in memory, and a second information is to just keep the ID of the root. Okay, so just if the root has identifier 5, then I want this 5 to appear as the second field of the label. Okay, and what's good about this is that it doesn't take a lot of space in memory. Like that's basically log n, where n is the size of the network. You have a distance, you have an ID that you're supposed to be encoded on log n bits. So it's not a lot of memory, and also it's simple in the sense that for any, maybe not any, but for many reasonable algorithms, just giving this to the node as additional information, this will be for free. This is not like something that you will use a lot of resources to compute. Okay, so that's nice. There's something you can give to the node for free. And what can you do if you're a machine with this information? What you can do is to run what I will call a sanity check. You will just check things like, does it make sense, this information, in comparison with what my neighbors have as information. Okay. And here I will use the labels that my neighbors have been given. So I will compare my local information with the information of my neighbors to check things. Okay. And this sanity check, it has 3 parts. The first part is to check that the distances make sense locally. So for example, here, the node, it has been given distance 2. So, and it is pointing to the node on the right. So this node should have distance 1, because if my distance to the root when I use the pointers is 2, it means that if I do 1 hop, then I should reach a node that is at distance 1 from the root. Okay, that must be this way. And just in the similar way, if I know that the node on the bottom has a pointer to me, then this distance should be 3. Okay. So just checking these distances, and note that I'm not interested in the distances of the other nodes that are not linked to the machine by pointers, because I'm just interested in the distance along the pointers. So I just check that if there is a pointer, the 2 distances, they make sense. Okay. So that's the first sanity check. Second sanity check, which is even easier, is just to check that everybody has been given the same idea for the root. Okay, if you're in a proper directed spanning tree, there is just one root, and so everybody should believe that the root is the same as the same ID. So, for example, here everybody believes that the ID of the root is 5. Okay, nice. And now there is one node that is a bit special, as we said before, which is the root. And so here the sanity check is the following. The 3 following conditions should hold together or should not hold at all. And these 3 conditions are the pointer points to the node. So it's like it's a loop, it's pointing to itself. The distance is 0. And the ID of the root that is written in the label is the same as the ID of the node. Okay, so these three things, either they are together and then it's the root, or they do not appear and it's not the root. Okay, so these are just sanity checks that you can do on this information. And again, I want to highlight that I'm satisfied with this sanity check because it's cheap in the sense that I just look at my neighbors as what they have in memory, and I don't need to talk about, I don't need to talk to nodes that are further away, like distance 2 or more. I don't care what they have. I just check that. Okay. So, okay, this is some labeling, some sanity check that you can do on the labeling. Maybe I could have invented something completely different. But actually, here is the gem. So the gem is that this is enough to ensure local checkability. So in a very intuitive level, what it means is that if you know that you have been given this information, and if the sanity check goes through, somehow you can be convinced that the structure that you have is a directed spanning tree. Okay, so this is just on an intuitive level. So now let's see what it means on a more a bit more formal level, because okay, and this will be like somehow the only subtlety of this talk. Like this needs to be you need to be a bit precise about these things because it's a bit counterintuitive. So what I mean by ensuring local checkability is the two following properties that I will call the yes property and the no property. Okay. The yes property is pretty straightforward. It's saying that if you have a correct configuration, so for example, you've been given you are living in a graph where the pointers, they form a spanning tree, then there exists a label assignment. There is a way to write the labels such that the sanity check accepts at every node. Okay, so this was property number one. And property number two, or the no condition, is that, and here is it's a bit subtle, it's that for every incorrect configuration, so anything you can imagine that is not a directed spanning tree, for every label assignment, there exists a node where the sanity check will not work. Okay, so what does that mean? That means that if you have an adversary that sees that you have something that is not a directed spanning tree, and you allow this adversary to write in the memory of every node some information, like the adversary thinking, yeah, I'm going to trick the nodes, putting this distance and putting this idea of a root, etc. So you allow an adversary to write this certificate, then you will be safe because there will be at least one node to realize that something is wrong, to realize that the adversary is trying to fool you, and a node where the sanity check will not go through. Okay, so it's really a worst case condition. Like you have an adversary that writes this thing, and still you can detect that something is wrong. Okay, so that's why it's called certification, because of this label, they certify that the output is correct. Okay. Okay, so yeah, I just claimed that that this property holds, but I have not proved it for this special labeling and spatial labeling sanity check that I've been explaining to you. So let me do a quick proof. So the yes case, I guess you're all convinced that if I identify the root and I write the good distances and I write the ID of the root to every node, then the sanity check is accepting everywhere. And okay, fine. Now for the no condition, and this is more tricky. So we said there are basically two ways in which a set of pointers can not form a directed spanning trees, and these are a cycle and disconnected configuration. So if you have a cycle and you allow the adversary to write the labels, then what happens? I will convince you that there is at least one node that rejects with the sanity check. And maybe you have already this feeling that actually the distances on the cycle, there should be something that goes wrong. Okay, so I will focus on these distances. And here is a one-line proof, which is, okay, consider the minimum distance on the cycle. So the adversary, it has written some distances, I look at the minimum, and then I claim that this node that has been given the minimum distance, it will reject. Why so? because it is on a cycle, so it has an outgoing pointer, and the next node on the cycle, the node it is pointing to, it has some distance, and this distance, if the sanity check accepts, it should be the distance of the node minus 1. And this cannot be because I took the minimum, okay? So that's like one-line proof that on the cycle, there is one sanity check that will reject because of the distance inconsistencies. And now a second configuration that is incorrect is, for example, here, when you have two trees, okay? So everything is fine except that you have two trees, not just one, okay? And now for this case, what I will do is that I will look at the roots of these two trees. So either these roots are rejecting because the sanity check does not go through, or it necessarily, in the second field of the label, it must be that they see their own identifier, okay? And now I will focus on the nodes that have identifier 11, okay? And these nodes, well, it's some set of nodes, and it cannot be empty, and it cannot be the whole graph, because we know that there is a node with ID 11 that has this, and a node with ID 5 that does not have this. And it's not every node. There is an edge between two nodes where one believes the ID of the root is 11, and one believes the ID of the root is something else, and then necessarily they both reject because of the second line of the sanity check. So yeah, that's the second case where things go wrong. So I hope I have quickly convinced you that this labeling and this sanity check that I've been describing, they have this property that I've been telling you about, this yes and no conditions. And well, in more general terms, if you are given for a given data structure or a property or something, I would say that there is a local certification if there is a labeling and, more importantly, a sanity check such that these two conditions hold, okay? It's not specific to spanning tree, it's just for any property you can ask such questions. And well, this is what is called local certification, or also, originally called proof labeling schemes, also called local for proof. So all these things are basically the same idea, which is to have these two conditions. Okay, fine. So this was somehow the gem I wanted to tell you about. But now you might ask, okay, this looks like a complicated definition. Like there are quantifiers, there are these two conditions. Why is this the right thing to look at? Why is it interesting? And I have two answers to this question. The first answer is that it's a tool for self-stabilization. So here I will be hand-waving and lying a bit. But, so a self-stabilizing algorithm, or should I say a silent self-stabilizing algorithm in the state model, it's basically an algorithm that can converge even if the memory is corrupted, even if an adversary comes and just replace the memory by something else. You believe that you have received a message from some machine that has ID 6 that was saying something, but actually that's not true. That's the adversary that has written this in the memory, for example. And one way to think about this is to think that it's an algorithm that can start from anywhere. Okay. And here I think there is a fun comparison with mini-golf. So basically, if you're working in something like the local model or the congest model, you are playing mini-golf with the classic rules, which means you start from somewhere you know, and you have a target, and you try to go there. And if you do self-stabilization, it's the same thing, but someone like just throw the ball in some adversarial place, and then you have to still hit the target, okay? So that's obviously much more challenging and maybe more fun. Okay, and one more thing about mini-golf is that in mini-golf, there are two things that you want to avoid. One is being stuck. So you cannot like reach your target because, well, you're stuck somewhere, like you do not take step anymore. And one more thing that is surprising to many people who have never played mini golf, but people who have played know that, is that sometimes you put the ball in the hole and then it jumps out, and that's horrifying. Okay, and in self-stabilization, there is something similar. So on a more serious note, there are two properties that you want to have in self-stabilization that are similar to what I've just been talking about, which are the following. So suppose you have this kind of strange memory configuration to start with. One thing that you want is that you keep taking steps. So maybe you are in a completely absurd world, but still you want to get closer and closer to a proper configuration. Okay, so you don't want to get stuck at some point where the memory is such that no node knows what to do. Okay, so you want to keep taking steps. You don't want to get stuck. And the second thing is that when you are in proper configuration, you want to stay there. You don't want to like keep using resources and computing another, I don't know, directed spanning tree or something. You want to stay there. So that's also called the silence property. And the good news is that local certification is exactly what you need for that, for these two properties. Why so? Because suppose you have a local certification of, say, directed spanning trees. Then you can build your self-stabilizing algorithm around that. How do you do that? So first you ask your algorithm to compute a local certification. So you ask it to not only build the output, but also build this additional information, these labels that will be useful to you. And the second thing is that you make sure that a node takes steps if and only if the sanity check rejects. Okay, so you will have the sanity check, and a node, if the sanity check accepts, it does nothing. It cannot change things. But if the sanity check accepts, then it is forced to do something. So of course there are some complications, etc. I'm really simplifying here, but that's the idea. Okay, so why is it good? Because once you are in a proper configuration, your algorithm has computed the local certification, you have the good labels, the sanity check accepts everywhere, you do not take steps, you've reached a good configuration, you're happy, okay, and you stay there. And if you are not in a proper configuration, it cannot be that the memory is such that the sanity check accepts everywhere, but that was the no condition from before. So you're sure that there is at least one node where the sanity check rejects, and you know that there is one node that will take a step, and so you keep taking steps. Okay, so local certification for this kind of self-stabilization, it's really something you want, that's really a nice tool. Okay. And the second reason why it's interesting, and it's maybe a bit more theoretical, but it's because it's a kind of local analog of the class of complexity NP. So let's take a look at that. So the class NP, it can be defined the following way. So it can be defined with non-deterministic Turing machines, but here I will take the certificate definition. So the problem is in NP, if there exists a polynomial time verification algorithm A such that for every input, the input is correct if and only if there exists a certificate C such that A, when it is given C and the input, it accepts. Okay, that's the certificate definition of NP. And now local certification, I've defined it with this yes and no condition, but I can define it in a more compact way, in the following way. I will say that there is local certification if there exists a local sanity check A such that for every input, so every configuration, the input is correct if and only if there exists a certificate assignment, so a function from the nodes to the labels, a way to label the nodes, such that the sanity check accepts everywhere, except at every node. So you see it's really the same shape, and it's not like a funny coincidence, like that's really something interesting and studied. Okay, so okay, these are two reasons why local certification has the right definition, why it's interesting, and so up to now, what I've told you is how you certify a directed spanning tree, what is local certification. And so this was what we know basically, and now I want to talk a bit more about like the present and then the future maybe, which is what kind of things do we do what do you do when you do research in local certification? And here, of course, it gets more personal. Like there are a lot of works that have been done, and I just do kind of selections of a few topics. Okay, so Topic one, so I said 5 research directions, so this is the first one. Topic one is to have bounds on the certificate size. So I said that these certificates, this label, this additional information, these are things that you store in memory in addition to your output. So you don't want this to be large. You want this to take little space. Okay, you want the cost of certification to be small. So you want the smallest labels possible, and for that, well, one question you might ask is, okay, for this example that we have seen, the spanning tree thing, is this login that I've been talking about optimal? And it is. So you cannot have a certification that uses smaller labels. And now you might ask, okay, I don't like spanning trees. I like whatever data structure X that is my favorite. What's the cost of certifying this? And that's a very good question, and people try to understand for various structures, how much does it cost to certify these things? What's the size of the labels? And then you can classify these sizes on this kind of arrow. And here there is something very interesting, is that on the right hand, where the sizes are small, you find properties that are the feeling of being quite local. For example, LCL that corresponds to, well, labels of size 0, for example. So colorings and these things, they feel local and they have small certificates. And on the other hand, on the right hand, you have things like isomorphism, like things that really feel global, and these use very large certificates. So somehow the size of the certificates, it's not only a measure of efficiency, it's also a measure of locality. How local is the thing I want to certify? Okay. So this was the first direction. Yes, thanks, Karen. Okay, and this was the first direction. And the second direction I want to tell you about is how do you get these certificates? Because when you do local certification, when you study this topic, you're usually thinking about like, oh, this labeling would be nice, and then we could do this sanity check, etc. But you don't focus on how you actually build these certificates. And that's like one of the directions of research in local certification, which is, okay, now that we know things about local certification, how do you adapt this into real algorithms, like real self-stabilizing algorithms? And here I want to highlight one question, which is the following. So we know that the space you need to certify a property, it's a lower bound on the space you need to stabilize on this property. Okay, you need at least the certification space. And moreover, we also know that these two things can be equal, so you can have the optimal space if you allow exponential time, okay, exponential stabilization time, etc. So one question is like, can we get the best of both worlds? Can we get polynomial time and use the optimal space, which is certification space? Okay, so that's like an intriguing question, and we do not have like general answer. Third direction, so this is in the direction of this link that I've made between NP and local certification. So of course, once you have one complexity classes, you want to have 1,000, and well, that's actually useful. So what people have been doing is to draw analogues between things that are in the centralized classic complexity theory and things that are in this kind of theory of local decision, of local things, local certification, etc. And just like in centralized computing, this is useful because it gives you insights about like, oh, this property, it's like harder to certify than this thing it's less local, it's more local, etc. So that's also like a great avenue of research, and there is like now very interesting works in like analogues of interactive proofs. So distributed interactive proofs, Arthur Merlin and these things, for example. Now, fourth direction, and this is like, I mean, it's not really a direction, it's like a set of questions. So during this talk, you've maybe been asking questions like, yeah, but okay, this model, okay, but what about port numbers instead of IDs? Or what about like, you look just at your neighbors, couldn't you look a bit further, like, that would also be cheap? All these kind of questions. And these are all reasonable questions, and answering them gives us information about local certification. So it tells you whether the definition is robust, whether a self-stabilizing algorithm could use some other kind of local certification, etc. So this is also very interesting. And now the fifth direction I want to talk about is about certifying the topology of the network. So for example, there is this theorem that says that can I be sure that the network is planar? Well, I can be sure with certificates of size log n. So I can certify with log n bits that the network is planar. And it's really like relevant for this talk because there are two solutions to do that, two independent solutions, and they both are related to directed spanning trees. So in one case, what you do is that you first build a directed spanning tree, or I mean, you certify a directed spanning tree, and then you mimic a kind of traversal, and the edges that are not part of the traversal, they should follow some local conditions. So that's a first technique. And the second technique is to certify each phase of the embedding, and then to gather all the information at the root and to check Euler formula. So in both cases, directed spanning trees are really essential. And I will finish my talk with this question, which is, I mean, in my opinion, very intriguing, which is, can you do this wide generalization beyond planarity, which is, can you certify minor closed graph classes with logging bits? Okay, and well, if you don't know what minor closed graph classes are, that's not a big deal. I mean, at the end, what the question is really is, like, is this notion of minor closed graph classes, which is a notion of sparsity from graph theory, is it like deeply linked with the fact that you can certify things locally? And if this were true, this would be really exciting. And if it's not true, I would be very interested too. And okay, that's all I have. So thank you for listening. And well, if you want to know more about local certification, here's one reference you can look at.